Hello. Let's go over some announcements before we get into the new material. First of all, your written summary for the demand estimation phase of the project, which includes your supporting calculations and some description of what your assumptions were. That should be uploaded to MU Online by 3:30 p.m. on the 2nd. So that's today if you're watching this video on the day that it's scheduled. We've discussed before what the project expectations are, and of course the handout for the project is uploaded online. So I'd invite you to look over that and be sure and meet that deadline. Next on the schedule of things to do is homework 8, which you can see the problem set there, and it's also on the course schedule which I provided at the beginning of the semester. That assignment should be uploaded no later than 3:30 p.m. on the 7th. And then also on the 7th, and this I've previously announced in the last recorded lecture, we'll have our second quiz of the semester on Tuesday the 7th. And the coverage for that is going to be classes 14 through 16, so that includes today's lecture. And I'm going to have an emphasis on the recorded lectures just to give students an added incentive to pay attention and try and make good use of those recordings. So, with all that said, I'll just add one other announcement, and that is while I'm away, please feel free to send me an email if you have questions. Since I'll be in a very different time zone, it may take me a while to get back to you, but I want to do my best to help you out while I'm away, so just let me know. Today we're going to be talking about channel efficiency and flow resistance, and this is a lecture that focuses a little bit on different shapes that can occur when we have open channel flow. The difference between a very, very wide river and a river that's more narrow and compact, and some of the interesting effects that arise having to do with roughness and having to do with accommodating the most flow. I'll add one other announcement, and that is that if there are any incidental references to dates or times in the rest of this video that seem to be a bit off, just keep in mind that the bulk of this recording was prepared in a previous semester, and so all you need to be aware of having to do with the announcements are here on the screen.
Yeah, it can get to be a mess. One of the things I wanted to show you, even though it doesn't fit exactly in with the content we're covering today, is a result of flow resistance. And that's what we've been talking about with Manning's equation, is what happens when a surface resists flow. And there are several different approaches that are taken to try and characterize the velocity distribution in a channel. Remember that when we've got water flowing downhill, the velocity of the water increases the higher away you get from that surface. So there's some sort of a velocity profile where the velocity of the flow close to the surface is small, and the further away you get from the surface, the velocity increases. Well, here's one equation that's been developed to try and approximate what the velocity is as a function of the distance from the bottom of the channel, y, and that's relative to a total depth of flow, d, where d is the whole depth of flow. And so if you wanted to find out what the shape of that curve looks like, then you can use the von Karman constant and this velocity distribution equation to come up with what the shape of that looks like. And so it can act a little bit weird when you get to really small depths. You'll notice that the velocity is actually negative. And so, depending on what variables you use, this equation performs reasonably or a little bit weird. But one thing I wanted to show you is the effective slope on velocity profile. And so the dark red velocity profile corresponds to a relatively shallow slope of 0.5%. And so you'd notice that the velocity up at the top of the channel is pretty close to the same as what the velocity is towards the bottom. But then the steeper the channel, so 2% slope now for the channel, you notice that there's a much greater difference in the velocity at the surface relative to the velocity at the bottom. And so that's one approach that's used to approximate velocity profiles. Sometimes average velocities are measured by finding the velocity at a certain depth. And so one rule of thumb kind of calculation is that if you calculate the velocity 4/10 of the, the velocity, 0.4 times d. Yeah, so if you know the depth of flow and you multiply that by the velocity at, this is actually not a numerical equation. This is saying that the velocity at a depth of 4/10 is sometimes taken as the average velocity. So if this was a depth of 1.0 in total, then you can go down so that you're at 0.4, so 4/10 of the way up from the bottom. That velocity would be taken as the average velocity, or you could take the velocity at 2/10 of the depth and average it with the velocity at 8/10 of the depth. And usually the way that they'll measure the velocity at a single point is they have what looks like a boat propeller. It's a little impeller, and they put it down into the water and it spins, and there's a reading that'll come up on how quickly it's spinning and what that corresponds to into the flow velocity. And so they'll just sort of take velocity at a couple of depths, and that's how they come up with the average velocity for flow in the channel, is just to measure it at a couple of locations with a physical measurement and then take an average. Another thing that doesn't quite fit in exactly with what's in the textbook, but is important for you to just sort of have a handle on, is what to do when you've got a floodplain and have to come up with a composite or an average end value. So let's say that flow ordinarily is in this trapezoidal channel, and the material that would be in a main channel, it might be like a compacted clay or concrete or just plain soil. So you'd have one set of end values associated with this trapezoidal channel, but then you're going to have different materials in the floodplain. You know, the floodplain can include grass, weeds, stumps, all sorts of trash, as we've talked about before. And so one of the common approaches for coming up with an average end value is the Horton-Einstein method. And in the Horton-Einstein method, what you do is you weight the end value based on the wetted perimeter. And so you would you'd multiply for each of these elements, you know, the wetted perimeter of element 1, you'd multiply it by the end value of element 1, and then you'd add up all the different pieces. So you'd now take this second part here, and maybe you'd have an average end value for this, where you've got all the trash and weeds and debris, and you would end up coming up with a weighted average that is based on the wetted perimeter. There are other approaches that base the end value on area, but the advantage of this, if you think about it, the resistance is applied at the surface, and so rather than weighting it on an area basis, it really should be weighted on the basis of the wetted perimeter, because it's that contact length that determines how much resistance is applied. All right, so this is Manning's equation, and if we have a certain end value that we can't change, we're forced to use a certain material, and we've got a given slope, S naught, how is it that you maximize the flow rate based on this equation? You want to have a big Q, so if you've got a certain N that's fixed and the slope that's fixed, you want a big Q with a big area and a small wetted perimeter. So the most efficient channel is one that minimizes wetted perimeter. And just to illustrate that, let's take these different shapes into consideration. What do all of these shapes have in common? All right, that's one thing. They're all rectangles. All right, the cross-sectional area for all of them is 20 square meters. Would you expect that all of them have the same flow capacity? Now, if you put that into Manning's equation, are you going to be able to get as much flow through this as through this one? I mean, even without knowing Manning's equation, if I just asked you instinctively, why is it that you'd expect the channel on the far left to not have as great a capacity as the one on the far right? What is it about that channel that makes you think you're not maybe going to be able to get as much flow through it? Why is there going to be more resistance? You're right, but why? Okay, there's a lot of, you've got a long wetted perimeter and it's narrow, so the flow just can't get away from the resistance. If you're thinking about it that way, where is it the flow has the freedom to move without being under the influence of that no-slip surface? Remember, the no-slip condition is that water doesn't just move without any resistance over a stationary object. Actually, the water at the interface of the object has the same velocity as the object itself. So we've got a certain thickness into the water that has the laminar sublayer, and even on top of the laminar layer, there's still resistance. Whereas here, in the center, it's far away from resistance, and so it's going to have more capacity because more of the cross-sectional area is far from resistance. And so let's do a spreadsheet example. I'm going to show you an illustration that just makes this point. How we know that we can find some cross-section that's best. Okay, so what I'm going to do is have the channel width B, Y is our depth, area, a wetted perimeter, a hydraulic radius, and then a flow rate in cubic meters per second. And for all of these, we're going to have the same slope of 0.01 and the same n value of 0.013. Let's go back here. Maybe I'll just copy this over so that I've got these to look at. Okay, so we're going to have one of them that is 10 by 2. So we've got one where the bottom width is 2 meters and the depth of flow was 10 meters. We have one that was 10 by 2 the other way around. We've got a 5 by 4 and we've got a 4 by 5. All right. I guess if I'm working from left to right, I should say that the bottom width was, this one was 5 and then 4. Oh, okay. There we go. Okay, so area is just going to be the B times Y for each of these, B times Y. So we're going to see that they all have the same cross-sectional area. And by the way, this process of what I'm going through right now is very similar to the last homework problem on your assignment. The last homework problem gives you a weird-looking shape. It says there's some channel that is straight on one side and inclined on the other. And you're going to try and minimize how much it costs to build this. And the solution I did for that problem actually is a spreadsheet solution where I try lots of different combinations to see what cost is the lowest. So as I'm doing this, keep in mind that this has a direct application to the last homework problem. So the wetted perimeter for these is, it's going to be simple for us to calculate the wetted perimeter here. It's going to be 2 times the depth plus the bottom width. So I'm going to do 2 times the depth and then plus the bottom width. So that's my wetted perimeter. In this case, you'd have to calculate the wetted perimeter of this inclined surface a little bit differently. You'd find out the height of it, the horizontal component, and find the length of it according to the quadratic equation. Okay, hydraulic radius is area divided by the wetted perimeter. So we can carry that through. And then finally, the flow rate is going to be Manning's equation. And so I need to type Manning's equation in here. This is what I'm going to be entering in for Manning's equation. I'm going to do the equation on the far right is how I'm going to write it. So equals the area to the power of 5/3 times the slope. I'm anchoring that to the 1/2 power divided by n. Also want to anchor that reference, and then divided by the wetted perimeter to the power of 2/3. Okay, so any questions on Manning's equation, how I've typed that in? Okay, so now I find out what the capacity of that channel is if it was this 2 feet wide, 10 feet tall. So I can just drag it down and find out that of the options that are listed, the most efficient is this one. It's the one that's 4 meters depth, 5 meters width. But that's just the most efficient of the options that are provided. I could probably do a little bit better. So the way that you maximize flow is by what? We have to, in this example, the constraint has been the cross-sectional area has to be 20. So I'm going to do another one where I'm forcing myself to have a cross-sectional area of 20. So how do I get the best flow rate? The smallest what? The smallest wetted perimeter. I'm going to find that with goal seek because I don't like to mess around wearing out my fingers. So I'm going to use, actually I'm not going to use goal seek, I'm going to use solver. Because goal seek you have to know what the objective is, and I don't actually know what flow rate I'm going for. Because in goal seek you have to say, all right, change this parameter in order to make some other cell equal to, and you have to type in the value you're going for. Whereas solver allows you to say, play around with this other cell in order just to maximize the result. And so I'm going to use solver, but it's the same thing. All right, so what I will do then is I have to get B times Y must equal A. And so how am I going to do that? I'm going to say that Y and B, okay, I'll have this be the one that I change. So I'm just going to start off with a guess value of 3. So I'm going to be changing this one. And therefore, Y is simply A divided by B. Because remember, area is the width times the depth. And so what I'm saying is area must be 20, and I'm going to allow solver to play around with what is the correct width, and so vary this. And then as it varies that, whatever it chooses, I have to have the Y be such that the area ends up being 20. So is everybody with me? I didn't pick that Y value. It's the result of a calculation. And so then the wetted perimeter is going to be the base plus 2 times the depth. The hydraulic radius will be the area divided by the wetted perimeter, and I guess I can just drag this down. It's going to be the same Manning's equation. It'll be area to the 5/3 power, slope to the 1/2 power divided by n, and divided by wetted perimeter to the 2/3. So Manning's equation is entered correctly. So now I go to the Data tab, and instead of what if analysis, I go to Solver, which is an add-in that you have to install separately into Excel. Click that, and now it gives me a few more options. Instead of having to know what value I'm going for, what I want, my objective is for this flow rate to be max. And I'm going to tell it should change B in order to make that come about. Now these other options allow you to say how close it has to be before the solution converges, but the default in this case is fine. We don't have to override the convergence criteria. So again, what we said is we want the objective to be maximized. And it will do that by changing the width. And so when it changes the width, it's also going to be finding the depth indirectly. So solve, and let's see what it came up with. We could get 208.8 cubic meters per second. That's the maximum. And what do you notice? The B and the Y. It looks like it's half. Yeah. I'm going to have it keep that solution. Okay, so it's keeping it. So what is B divided by 2? Well, there it is. It's our depth. And so the most efficient rectangle is a half square. And that's what we get to on this next slide that says there's different shapes. Let me just jump to this slide here, which says there's different shapes that have a certain best hydraulic efficiency. And for a rectangle, the best rectangle is a half square. We'll come back to this in just a minute. So since we mostly do trapezoids, trapezoids are the most common engineered channel. The best trapezoid has a kind of an unusual shape because the side slopes are much steeper than ordinarily we'd go for. You know, a pretty common side slope would be 1 vertical for every 2 horizontal. But the root 3 divided by 3 is actually, I think, 0.577. And so that actually ends up being pretty steep, the side slope there. And so it would only be common for us to go for this best trapezoidal channel if we were working with a concrete lined channel. And usually it's not so critical for us to maximize efficiency that we'd go to all the trouble of making it that shape. But technically speaking, the way that you actually get that shape is it's the channel that if you draw a circle, it's the trapezoid that best approximates a half circle. And so it will intersect the trapezoid at the bottom, in the center, and on the sides as well. The circle, if you think about it, remember what we're trying to do is we're trying to minimize wetted perimeter. And the circle has the greatest interior area per perimeter of any shape. And so the trapezoid that gets closest to approximating the circle is the one that will have the most flow per unit of wetted perimeter. And so it has the characteristics of, you can calculate the wetted perimeter as a function of the depth y, the bottom width as a function of y, the cross-sectional area, the t value is constant, and the hydraulic radius is just area divided by wetted perimeter. And so the interesting thing about hydraulic radius is it's just the depth divided by 2. So that's kind of a unique thing.
What's M up there?
M?
Yeah.
Where do you...
B equals
I'm not seeing it.
on the first.
Oh, here? Oh, sorry. It means T. T, yeah, because if you actually look, I took this figure from another text, and the way that they defined the side slope there was M instead of T. Yeah, I'm glad you noticed that. I forgot to change it. So let me just do this. Copy, paste, and put that right back up there. 2 times, what was it? TY. TY. All right, thank you for noticing that. So where it said M for the top width, change that to say T instead. So here are some other shapes that are like most efficient. And by most efficient, again, what we're going for is the shape that gets closest to the half circle in order to maximize the area that is away from the resistive surface. So here is the best triangle. It is a triangle that has a 90-degree angle down here because it's the one that allows us to put the most of the circle in there. And let's try this out. This is a combination of best section and Manning's equation. So hopefully you've taken the time to figure out how to solve equations on your calculator because, like I've said before, there's no escaping that need. What will be the flow depth? What is the y if we're going to do the best triangular cross-section, and we know the flow rate that has to be accommodated is 2.5 cubic meters per second. That's what we're trying to convey from point A to point B. We're going to use concrete that has an N value of 0.013, and it's a 1% slope. And so what will be the flow depth? So to solve this, use Manning's equation, and here are the formulas you should use for area and wetted perimeter. Use the triangle. Area is y squared, wetted perimeter is 2.83 times y. Feel free to collaborate with your classmates on this as you're working through it. In this, yeah, T is top width, right. All right, so let's take a look at where we're at with this one. We're solving Manning's equation, and we need to substitute in the formula for area and wetted perimeter in terms of the unknown depth. So Manning's equation ordinarily would be a to the 5/3 divided by n perimeter to the wetted perimeter to the 2/3 power, and then all of that is sloped to the 1/2. For the triangle that I've got here, which is going to be a triangle with a 90-degree angle at the bottom, the area is the depth squared, and the wetted perimeter is 2.83 times y. So I just put those formulas directly into Manning's equation, and now I need to find the y value that gives me the right-hand side equal to 2.5 cubic meters per second.
Okay, so now that we've got it set up, let's try solving that on the HP calculator here. I'm going to use the numerical solver, and I'm going to solve an equation, and I'm going to enter the equation in with the equation writer. And I know that the flow rate is 2.5. That's equal to y squared to the 5/3 power. So I'm going to do y squared, and then that is to the power of 5/3, and then that is divided by 0.013, which is my n value, times let's see, 2.83 times y, and that is to the power of 2/3, and then all of that is times the square root of 0.01. So 0.01, 0.01, oh no, not the whole thing, just that to square root it. Alright, so we've got the formula typed in, and I'm going to solve for y, and it tells me 0.851. So that's the depth that we're going to experience for the conditions that have been described solving for Manning's equation.